postdoc researcher there, and I'm happy to chair this session. And there is a form, by the way. In the end, we need to everyone attend this. We need to sign this form, so remember to do that. So this session we have Dr. Sam Stanier, and before give the presentation, I would like to give a very short introduction of Dr. Sam. And Dr. Sam Stanier is associate professor at Cambridge University. He obtained his PhD degree from Sheffield University in 2011, I think. And after that, he went to University of Western Australia in the working in the Center of Offshore Foundation System. And he did a lot of work in the offshore engineering related to like oil and gas and offshore energy system. And in 2018, he joined Cambridge, and his current research is basically focused on the whole life design of soil and geostructure, and also using, I think, a PIV technique, which he will talk today. So I guess later Dr. Sam will teach you how to become a good photographer in the centrifuge modeling, every detail. So Sam, the floor is yours.
Yeah, thanks very much for that introduction. This is I guess a short course that I've given a number of times, and I give it on an annual basis at Cambridge to our onboarding PhD students that are working at the Schofield Centre. Basically, what I'm going to give you is an introduction to PIV, or particle image velocimetry, sometimes known as digital image correlation. If you see those two terms, they're interchangeable. So what am I going to cover in this short course? Well, I want to try and answer a number of questions. Firstly, very briefly, what is particle image velocimetry? I'm not going to go into any great depth about the equations or the details of the algorithms. I'm going to tell you at a very high level what variants of algorithms are available to you that you might use. And I'm going to look very briefly at what you can do with it. I'll give some example experiments of measurements around various geotechnical structures. We'll then go into detail about what equipment you would need, so considerations about what an appropriate camera might be for a specific application, whether it's quasi-static or dynamic. Lighting, we'll consider control aspects, so how you control the camera and lighting. I'm then going to talk in quite a lot of detail about how to set up a PIV model test. In fact, this makes up the bulk of this session. And what I really want you to take from this session is that most of the work in PIV modeling is about the preparation. Okay, the final bit at the end, for me, in this whole course, is just a couple of slides. So how you actually run a PIV analysis once you've got your images is a very short component, because frankly, if you've done a good job on the second to last bullet point here, the last part, running the analysis, is easy. Get the setup wrong, get the preparation wrong, and your PIV analysis will turn into a nightmare. And I'm going to talk through various reasons why that might happen to you if you don't prepare properly. So first of all, what is particle image velocimetry? Well, in a nutshell, we've got a couple of images. We might have a sequence of images, but for now we'll stick with two. We discretize this with what we call a mesh. Here we've got these little yellow squares here representing subsets of the first image or reference image. And what we do is we then look for the position of those subsets in subsequent images in our sequence. And we use a cross-correlation function in order to interpret what the displacements are to the nearest integer pixels. Once we've got the displacements to the nearest integer pixels, we might also do some sub-pixel refinement of the displacements. And at the end, what we end up with is an array of vectorial displacements. Of course, we can take derivatives of that displacement field in order to get the sort of strains that Yanis was showing you in a couple of examples earlier. So the third column here is really where the action is in terms of the algorithms that we're using to define these measurements based on these image sequences. And there are various different types of algorithms. I'm going to introduce a couple today from a very, very high level. So what can you do with it? Well, let's have a look at some basic PIV examples for a moment. On this example here, we've got a half jack-up foundation pressed up against a perspex window. It's punching through a layer of sand overlying a soft layer of clay, a sort of classic creme brulee problem. And we're using the PIV measurements to validate some large deformation finite element modeling we performed in parallel. You can also look at pipeline breakout. You can look at the flow of soil around caisson stiffeners. You can look at failure mechanisms around plate anchors, skirted foundations, and you can even look at the evolution of shear bands on this translating retaining wall problem here. So it's really it's a nice technique for delving into what the mechanics are around our geotechnical structures at failure. Now, and as Yanis noted, in almost all of these cases, we've got a planar cut across our model. They're not all plane strain problems. The caisson stiffener problem is modeled in plane strain. The ploughing and cutting problem is modeled in plane strain. But actually, most of the other problems here on the top of this slide are a half-space axisymmetric problem, right? So we're taking a circular foundation, cutting through half of it, and then modeling the deformations on that plane. Here's a slightly more exotic example. So here what we were trying to do shortly before I left UWA was to model the installation process in flight of a half suction caisson against our Perspex window. So this was a test performed in the UWA beam centrifuge, which you can see on the left. And effectively what we did was we put another strong box inside the main strong box and then set up a camera gantry with a couple of cameras attached to it. You'll notice here that one of the cameras on the left is labeled the micro camera, one on the right is labeled the macro camera. They've got different lenses looking at different fields of view, one more zoomed in than the other. And we'll look in a little bit more detail a little bit later on as to the potential impacts of that system. The real challenge with these experiments was trying to keep the seal around the edge of our caisson as we sucked it into the sand. And this was a very challenging experiment. We did eventually get some good results out of this, but I think we probably performed 3 or 4 times as many tests as we've subsequently published. We lost the seal on this caisson really quite regularly. So here's a closer look at my camera fields of view. On the right-hand side, I've got the macro camera view. We're looking at the overall model. So we're getting a picture of the entire deformation mechanism at a modest image resolution. And then on the left-hand side, we've got the zoomed-in micro camera view, which gives us 20 times the macro resolution for where the action's really happening in and around the tips of the suction caisson. So in this case, we wanted 2 cameras in order to get these 2 views in parallel, because if we'd gone for the sort of halfway house in between, we'd have lost the detail that we gain on the left-hand side, and we'd have lost the overview that we get on the right-hand side. Here's an example of some of the results you can get from these measurements. So on the left, you can see the progression of the normalized resultant displacements that come from the vectorial displacements we've calculated within the image sequence. We can then take derivatives of that displacement field and get some measure of strain. In this case, it's the total accumulated shear strain. And you can also look at the volumetric strain here. So you can see areas in this sand that are both dilating and contracting as this suction caisson is effectively pulled in by the underpressure beneath the top cap of the caisson. So let's have a closer look at the equipment that you might need to perform a PIV experiment. Now, first of all, it might seem obvious, but you need a camera. Sort of questions you might then start asking yourself, well, what type of camera, what resolution? Should I worry about distortions? Is the lens choice going to affect that? What sort of sensor might it have? You're going to need some lighting. Typically, centrifuges are installed in, dark basements. There's not a lot of natural light. Natural light's often not very favorable anyway because it's varying, especially as the centrifuge package is spinning. So actually, ideally, what you want is a dark room with very controlled and focused lighting. So you're going to want to look at that. You might want to control the lighting in flight in order to adjust the field of view that you get. In terms of control and acquisition, you need to control your camera, control your lighting, acquire images from the camera. You're very likely to want to synchronize the data stream coming from the camera, which is the sequence of images, with other measurements that you're making. Right? So you need to find a way to take the timestamp from the images and incorporate that in your other data sets. And there's naive ways of doing that with system times that are in the file timestamp, or there are slightly more difficult ways of getting the image time actually into your data stream directly, which I'll talk about in a moment. In terms of our camera, we've got a number of considerations: size, image quality, robustness, and also the type of connectivity that the camera has. And in the early days of PIV modeling, people tended to use compact cameras like this old Canon S90 here. And I picked this one specifically because we have a bunch of these still floating around at the Schofield Centre. They're reasonably compact, good quality images. They are quite fragile though, because they have a moving lens assembly that isn't particularly well supported. So you have to make sort of convoluted lens supports in order to support this camera in flight. But the biggest problem with these cameras is they've got really poor PC connectivity. They tend to have a proprietary interface, which is very difficult to use and manipulate in flight. Then you can look at the sort of cameras that I started out with when I was modeling at 1G at the University of Sheffield, a DSLR. They're quite bulky, but they get really good quality images. You can have very precise control of the quality of the output. Downside for a centrifuge application is there's a lot of moving parts. And again, you're stuck with the same proprietary USB connectivity and lack of control. The type that most people have moved to now is what we call a machine vision camera. They're very compact, very robust. They produce good quality images, not quite as good as a DSLR, but depending on the lens you choose and the quality of lens, you can get good images. But the real plus side is they've got excellent connectivity. So you can get Ethernet variants or USB 3 variants of these cameras these days, and they're super easy to interface with. A lot of them come with Python libraries, and most people these days, not being antiquated like me, are very comfortable in Python. And with a few lines of Python code, you can be acquiring images from these cameras very straightforwardly. So I strongly recommend, if you're buying some equipment, look for the sort of compact machine vision type camera. The only real downside is you don't get a live field of view on the camera itself. So on the back of the compact camera and the DSLR, you tend to have a little LCD screen that you can use to sort of scope out the field of view when you're assembling your equipment on your centrifuge package. You don't get that with this, which means you've got to wire everything up to your control room in order to be able to view what the camera sees as you're setting up the model. It's a small price to pay. In every other way, these cameras are the best choice. So we look for a machine vision camera. We go to, I don't know, any number of vendors of machine vision cameras, and we start searching for cameras with a particular resolution and frame rate, depending on your application. And a question that you then have to ask yourself is, what sort of sensor do I want? And there are two main types of sensor, a CCD sensor and a CMOS sensor. Now, nearly everybody's probably got a CMOS sensor in their pocket because almost every mobile phone sensor these days is a CMOS sensor. But there is some argument to be made that a CCD sensor is slightly better because each of the pixels is effectively converted from a photon to an output voltage using a single amplifier. So they're slightly more consistent than a CMOS sensor, which has individual amplifiers for each of the pixels. So there's a small argument to be made for CCD sensors here. This was probably more true 10 years ago when I initially made these statements than it is today. So this is perhaps less of an important choice, but I would still err towards a CCD sensor if you can find one. The more important choice, and this one is critical, is whether you have a rolling or global shutter. So if you have a rolling shutter, what it means is you're going to read the pixel charges line by line across the sensor in some way. And what this means is if you've got a very dynamic field of view, you get a time lag between reading the first and the last pixel, and then as a consequence, you get distortion of that moving object in your image sequence, which is very bad. You really don't want this. It causes decorrelation, which makes it very difficult for the PIV algorithms to give you meaningful data. What you really want is a global shutter mode where you get simultaneous reading of all of the pixel charges. There's no time lag in the recorded image, and you essentially get an instantaneous snapshot. So this choice is really critical. You'll find in general that rolling shutter cameras are cheaper, but you really want to find yourself a good global shutter camera. Here's an example of the camera that we used heavily at UWA. It's an AVT Pro Silica GC2450C. There are now much better cameras than this, but at the time this was pretty much the state of the art. It was 5 megapixels. You could get it in either color or monochrome. It had a CCD sensor, global shutter, an Ethernet connection, and as a consequence of that Ethernet connection, you got a sort of pseudo unlimited image capture range, depending on how big your solid state disk was on your flight computer. And we were using this routinely to get 15 frames per second. And this is really good for quasi-static problems, right? All of these dynamic people here, like Yanis with shakers, It's not really the camera that they would want, but for most of the stuff that I did, this was ideal. And in fact, now we've bought an equivalent of this, but a modern equivalent at Cambridge that has 12 megapixels, is USB 3 instead of Ethernet connection, but it's still very similar, frame rates of about 30 frames per second. So good for quasi-static tests. If you're in the dynamic range, you want to find yourself something with much higher frame rates. The price you pay is that you have much lower resolutions. Consequently, this is the one that we had at Cambridge until recently. It's since been upgraded, but this one you can see much more modest resolution, 1.3 megapixels. A cost associated with that very high frame capture rate is you tend to have to use onboard memory, and so you've got a limited number of frames, and consequently the frame rate is also linked to the image size and the onboard memory that you have available. So again, these days there are better cameras than this, but you can see what I'm looking for here. I'm looking for a camera that's got a global shutter, decent resolution, the right form factor, and the right connectivity. Okay, they're the key ingredients. So you've gone out, you've bought a camera. You can also specify a lens with a particular focal length in order to get your field of view approximately right with respect to your model position and camera position. And that lens is inevitably going to induce some distortions in the images. Okay, the distortion we can quantify in terms of barrel and pincushion distortions, and we can fit simple mathematical models to account for these distortions as a function of the coordinates of the pixel that you're looking at within the image. So what I'm looking at here is taking a planar grid on the left-hand side where we've got no distortion, and then I've superposed some distortions here to give you an idea of the sort of distortion that a lens would induce. Now, in truth, this doesn't have a huge impact on your PIV measurements, as long as one thing is true, and that what needs to be true is that your displacements are small. Right? If your measurements are staying in the same location in the image, this distortion doesn't matter, because you're going to have the same distortion in both your reference image and your target image. Okay? But the minute you have soil moving from one side of a model to the other, the distortion is going to change between the images and the sequence, and all of a sudden you're going to entrain errors in your measurements. So in principle, what I say is photogrammetric corrections are a nice thing to have. If you have sufficient information to reliably account for these distortions, you should correct for them. And you can do that using either fixed control points, or you can pre-calibrate the camera prior to doing your test. So here's what an array of control points might look like. And basically all we've done here is we've taken the milled Perspex window to our machinist and said, drill us a bunch of holes in this at known positions. We'll backfill them with a little marker that we can take the centroid of, so a weighted average coordinate position of each of the points, so that we get a coincident set of pixel and object scale measurements. In this case, it would be millimeters. So we want an array of values that give us coincident pixel and object space positions. And that allows us to perform a translation from image space to object space. Now, the downside of this is you can see that we include quite a significant part of the model here. All right, we don't want to be taking measurements right in close to each of these markers, because we're going to get static parts of the displacement field. The markers don't move, and so effectively what you get is decorrelation as a consequence of that. So actually these days I've moved away from using these control points entirely. I'm now suggesting people just pre-calibrate. And I think the idea of using control points is really a sort of hangover from people's concerns about using compact cameras in the early days, where you've got those flexible lens assemblies, and when you spin up the centrifuge, the lens sort of settles into its cradle that's supporting the lens. And in the early days, people wanted to account for that because it would genuinely create movements of the camera as you ramped up. These days, with these machine vision cameras, when adequately supported, the lenses don't move at all. And subsequently, I'm now suggesting that people just pre-calibrate the camera. So do some experiments on the lab floor with your apparatus all set up, get the distortion coefficients for whatever photogrammetric correction model you want to use, and then simply use that consistently on all of the images that you get out. And that way you don't have these occluded points peppering your field of view, which get quite annoying, especially as you get to points like this. I mean, this target marker being aligned with the corner of the caisson is a really bad idea. That was a mistake on our part. We should have made sure that this column of markers was well away from our area of interest. So don't make the same mistakes that we've made. We've made them for you. You can learn from those and do better experiments. Lighting. Back in the day when I was at UWA, these were frighteningly expensive. These are like $1,000 each, these LED panels. But they were very good. They come with diffusers, which soften the lighting and make it more evenly illuminated. You can also get polarizing lenses for these lights. They're sometimes useful if you want to minimize the effects of reflections. These days, these are as cheap as chips. You can get knockoffs of these LEDs for a few $100s on Amazon, even less than that, actually, in some instances. In essence, though, what you're aiming for is you want a lot of light and you want it to be as uniform as possible. So the more LED panels you've got and the more diffuse you can make the light that comes from, the better, because you can minimize reflections. And a little bit later on, I'll show you some examples of critiques of people's setups, and I'll point out some of the issues that can be caused by reflections from lighting. Control can be provided in a number of ways. We use this GardaSoft LED control unit. It basically has a TCP/IP Ethernet connection that you can tap into, send messages to, and adjust the lighting intensity to one of a number of panels. And in this case, this controller can control 2 channels. Again, this is a nice to have. You can set this sort of system up manually as well ahead of time. But occasionally you might want to adjust things in flight. And so this is a nice thing to have. Perhaps more importantly is the camera control system. Nearly all machine vision cameras will come with their own proprietary software, which will allow you to get going and capture images quickly. The downside of those proprietary softwares is they don't give you any means of integrating the timestamp for each of the images with your other data set. And so what we did at UWA was write our own software in LabVIEW that would take the images for us, and it would stream the image time for each of the images to the other software we'd written to actually record data from all our instruments. So for every measurement on all our other instruments, we had an indication of what the last taken image name was, so that we could then plot the data in a temporal sense, and for a specific point, an interesting point in the experiment, we could go and find the appropriate image with ease. That was a really nice facility to have, and we've created something similar at Cambridge as well. What you really want, though, this is a key aspect of the camera capture software, is you want a live preview. You want to be able to see what's happening as you ramp up. You want to see that you've got nice contact between your model and the window at all times as you prepare to trigger your experiment. And so that, that live stream is the main aspect that you want from this software. Okay, so we've had a shopping list. We've gone and bought a bunch of equipment. Now we get to the hard part. How do we set up the PIV test? And as I said at the start, if you get this right, the analysis is trivial, really easy. Get this bit wrong, and the only solution is to go back in the lab and start again. And I get a lot of emails from people saying, oh, I've got these images. Can I adjust them? Can I change the image? What can I do with the image? Can I pre-process it? And my answer to them is not the one they want to hear, but it's almost always, there's not really much you can do. Once you've taken the images, you can tweak at the edges a little bit. Some people claim they can improve the output from PIV analysis by pre-processing the images, but I don't really believe it, to be honest. So what's the general procedure? You should start by assembling your experimental system. So mock up exactly the experiment you want to do, ideally on the centrifuge package. For us in Cambridge, it's easy because the swing arms are detachable. We can build the box, camera, gantry, lights, the whole shebang. We can build it prior to the experiment. You want to play around with adjusting your camera position to get the required field of view. That might take some time. And as I said, if you're using machine vision cameras, you're going to have to link back to the control room, go and have a look, adjust it a little bit, go and have another look. A pair of walkie-talkies and a couple of people often come in handy for this and make the process much quicker. Once you've got the camera position right, you then want to arrange the lighting. And it's important you do the camera position first and then the lighting so that you can then minimize the impact of reflections and you can try and get the illumination as even as possible over the whole field of view. If you subsequently move the camera, you might need to adjust the lights again as well, right? So this is why I'm saying get the camera position right first, then sort the lights out. Once you've got the lighting nicely, evenly illuminated, you can then set the camera aperture and exposure time to suitable settings. I'll delve into that in a bit more detail a bit later. And then this, for me, is the key step. You want to check your image texture by assessing the quality of the image for PIV purposes. There's a number of algorithms you can use for this. We've made it easy with the GeoPIV code that we've released because we calculate a lot of these measures automatically in the mesh output file. It's critical you do check this step, and a lot of people are reluctant to do it because it means actually making a full model, and seeding a clay model or raining some sand with the right texture is laborious. Refining the image texture is a laborious process. For me, it's critical, but you only have to do it once. I think it's worth putting the time in to get right. So as I said at the end here, if necessary, refine your image texture to optimize image quality. And what you'll tend to find is you might do this once for one experiment, and from that you'll get a good feel about how the makeup of your soil is going to influence the output image texture quality. You'll get a feel for how much seeding you need, and next time you can probably short circuit the process and go straight to the right answer by experience. But I think the first time it's important to do it rigorously, and I'll show you a technique for doing that later on. So here's an example of assembling your experimental system. On the left-hand side, we've got a drum centrifuge example with a small, compact, strong box. On the right-hand side, a slightly larger setup in a beam centrifuge with our master micro and macro field of view cameras. Then we're adjusting our camera position to get the right field of view. So again, we're fiddling around with the camera positions here to get this micro and macro view right, trying to minimize the distortions by keeping the cameras perpendicular such that the sensor of the camera is as coplanar as possible with the target plane that we're trying to image. That'll minimize the lens-induced distortions from the camera positional errors. The question you really want to ask yourself at this point, though, and this is critical, is how large can your field of view be? Okay? And this depends. It depends on the resolution of your camera. Let's take a step back for a moment in trying to answer this question. Let's think about how the PIV computations generally work. And as I said, you've got an image, a reference image, you've got a bunch of subsets that you've discretized. We're going to go and search for that subset in subsequent images, and we might have a slightly enlarged search region here. And from that, we're going to get this map of the correlation or cross-correlation function. And this peak here indicates the nearest integer pixel values for the displacements of our subset between our reference and target image. So that's fine, but we've only got integer pixel displacements because our image coordinates are integer pixel values. So classically, what people would do is they would also take the 8 nearest neighbors correlation coefficients, and they fit a bicubic interpolant function to that in order to interpolate the peak of the interpolated bicubic surface. Right? This is classical subpixel refinement that you'd find in the early GeoPIV code. And that's fine. It works reasonably well, but only if you've got what I would call suitable particle image size. And what I mean by that is how big the features that make up your texture are. Okay? And the hypothesis is that if this particle image size is small, if the grains of our sand are small relative to the pixel size, then this correlation peak is going to be really peaky. And as a consequence, this bicubic interpolant surface is going to effectively bias the output from our analysis. So let's have a look at that in a bit more detail. The way to look at it is to take some synthetic images. So what I've done here is I've defined different D on P or particle image sizes, where I've got a white blob that is representing a sand particle or a piece of texture provided in my clay model, and I'm going to move it by some subpixel amount, and I've got different sizes of particle representing different camera resolutions, if you like. So this dot has a Gaussian intensity distribution. As I said, I subject it to a subpixel displacement, and then I calculate some cross-correlation function. In this case, it's a zero normalized cross-correlation coefficient. I fit my bicubic interpolant to it in the classical way. I take my 8 nearest neighbors and I interpolate to find the peak of that function. And what I find is when my particle image size is small, so my particles are small relative to the pixel size, I get this crazy biasing. right? And the displacements start to bias towards the integer pixel values hugely. Where this is problematic is where we start taking derivatives of the displacement fields, because we start to get funny strain features that look compelling. They look like really, highly amplified shear bands. They at first, I thought they might have been real. It took a long time to work out that we should do this analysis to check that they're not real. As the particles get bigger relative to the pixel size, we get closer to a line of equality where our applied displacement is practically equal to the inferred displacement. These are classical bias errors coming from this particle image size. So what you want to make sure is you've got sufficient particle image size. All right, a value of 1 isn't really going to cut it here. A value of 2 is getting better, but really we want a particle image size of about 4. Any more than 4 pixels per particle, and we're wasting resolution. We can see that there's not much difference between the D on P of 4 and the D on P of 8 line. So less than 2, you're getting what we call peak locking, where you're going to get these biasing displacements. From about 4 and above, we have less of a problem. If we look a bit more closely at a cross-section of our bicubic interpolant, you can see the mechanism here, this actually happening. Okay, so I've got 3 different displacement magnitudes here on the right, minus 0.4 pixels, 0 pixels, and 0.3 pixels. And you can see in these 4 snapshots here for different particle image sizes, 1, 2, 4, and 8, you can see the differing degrees of bias, which is the dashed vertical lines and the solid vertical lines diverging. In a perfect world, they should be on top of each other, but you can see as you reduce the particle image size, you get an increasing degree of bias. So that's just another view of exactly the same analysis we had on the previous slide. So just to reiterate, you want this particle image size to be at least 2. And later on, I'm going to give you a couple of convenience equations in terms of the model geometries, the particle size, the D50 value, that will allow you to calculate this D on P value very quickly as you put together your experiments. Now, for me, it's critical that D on P is greater than 2. Ideally, it should be around about 4. Here's a more representative example of this peak locking problem. So it was okay doing this on one synthetic particle, but people would say, well, this is all very theoretical, but how does this map to the real world? And again, we wanted a synthetic problem so that we weren't plagued by other errors feeding into the analysis. So we took this Flamand elastic displacement field here. We've got smoothly varying displacements, and as a consequence, there's no displacement discontinuities. And that would mean, in principle, that there should be smoothly varying strain fields beneath this point loading problem. What do we get, though? Well, if we take some synthetic images again, this time we're going to pepper a black background with thousands of these white Gaussian dots, again with different diameters representing different particle image sizes. What we end up with is a bunch of strain fields, and they look a little bit like this. Okay, so what I've got here is, again, moving from left to right, we've got increasing particle image size. And you can see these funny worm-like trails, these concentrations of, in this case, shear strain here. And you can see that the concentrations in shear strain are at the exact same locations as we get decorrelation. Right? And this is this peak locking problem in action in a more representative example. So what happens when you try and capture too large a field of view? So your D on P value is too small. You get a breakdown of the subpixel refinement process. Your displacement's biased to the integer pixel values, and your derivatives become meaningless, or at best meaningless, at worst, totally misleading. And here's an example of a real-world experiment. Right, and this really is the experiment that set me off on this problem, because we had David Muir-Wood from the University of Dundee at the time visiting us at UWA, and he'd come to us with this picture on the left here, and he said, I'm not sure I really believe these vermiculate worm trails of strain. Can this be real? And we scratched our heads for a while, and in the end, we came up with the story I've just told you. And in essence, the proof was just that I went into the algorithm, I turned off the subpixel refinement, and I found I got pretty much the same result. So the left-hand side is with the subpixel refinement in the classical PIV approach, and on the right, when I turned it off, no difference. And all of a sudden, we're like, oh, we've got a big problem here. Okay. Now, this actually got published on the left-hand side. So it was sufficiently compelling that it got through a peer review process, it was published. At the time, it looked like a plausible result. And part of the reason why it felt plausible was this was an experiment performed on glass Ballatini where all of the particles are exactly the same diameter. So perhaps in principle, this could happen. What we asked ourselves at that time was, could a more sophisticated PIV algorithm perhaps alleviate this problem? So it really catalyzed the development and then subsequent release of what we call GeoPIV-RG. It uses a totally different genera of subpixel refinement algorithm that turns out to be more robust to these sort of peak locking problems. And in essence, what it does is it says that we've got a bunch of parameters that control the displacement and deformation of our subset. We're going to assume we don't know them. We're going to use our integer pixel estimate of the displacements to precondition that problem. And then we're going to use inverse compositional Gauss-Newton techniques to iteratively refine down to the optimal set of parameters to describe the subset distortion. And in addition to being more robust to this peak locking problem, it also means that we can have strains occurring within our subsets, which reduces the degree of decorrelation. And this resulted in about a factor of 10 improvement in the measurement precision. So just to recap, here's the classical PIV approach. All we're solving for is the U and the V displacements in pixel terms. We do that firstly to integer pixel values, and then we refine it with that peak fitting bicubic interpolant approach. And so our subset is simply translating. If we get any deformation or distortion, we get rapid decorrelation, which is what I'm indicating on the right-hand side here. And so with the new approach, because we've got these additional terms, du dx, dv dy, du dy, and dv dx that we're solving for with this iterative approach, we've now allowed our subset to deform, and as a consequence, we get much slower decorrelation with respect to the strain in the model. Right? So more robust analysis, but we're also getting a more reliable analysis from this addition. Here's an example of the improvement in precision. So this is looking at subpixel displacements. There's about an order of magnitude improvement here. Rotations are huge because we've got the additional first order terms. We can get almost perfect tracking of rotation now, which has a huge influence at large rotation values. And then similarly for vertical and shear strain, you can see we've had a significant improvement by accounting for the deformation. And that improvement persists all the way through the strain range that we might be measuring. The effect on real-world performance can be seen by comparing the left and right-hand sides of this experiment here. So we've looked at exactly the same sequence of images. We're plotting the accumulated shear strain here, and I'm cheating a little bit because I've plotted it in a logarithmic scale in order to amplify the effects in the far field. But you can see there's a lot of noise in the original algorithm in the far field on the left-hand side compared to that you get from the new algorithm on the right. And this perhaps isn't important to a lot of people. All right? If you're just looking at PIV technique as a way of getting a qualitative appraisal of what's happening in your model, this doesn't matter. But the minute you want to try and quantify the behavior or use these strain measurements to infer constitutive behavior, as some people are starting to try to do, then this far field information becomes really, really important. And you want to minimize the noise in those regions. So I should show you briefly that these more sophisticated algorithms do suppress peak locking, but it's only to a particular degree. So I've said yes or no to this question here. And what we find is that we can relax our particle image size ratio just a little bit. And in fact, a D on P ratio of 2 works out to be about sufficient for these new genera of algorithms. So here's an output that corresponds to what we got for the classical algorithm before. And you can see that at D on P of 2, we've pretty much got the picture we'd have expected. There's a small amount of decorrelation that you can just see there if you've got a keen eye. So if you're pushed for resolution, if you use the right algorithm, you can squeak D on P down to 2. Really, though, you should probably still be aiming for 4. So the new algorithm has helped. It's not really fixed the problem. If we look at the real-world data, then we can see that the situation is also improved, but not totally fixed. So this is the same glass Ballatini experiment, and what you can see now is in the far field, most of the evidence of those vermiculate worm-like strain features has disappeared. There's still a little bit of evidence of them being in existence there, but it's mostly gone. So the algorithm has helped a lot, but it's not the total answer. So in conclusion, the subpixel refinement algorithm is more robust. As I said, there's a little bit of evidence of the existence of those features in the far field, but it's mostly disappeared. So as we're setting up our model test, you want to be checking this d on p value, and you can use these two equations on the right-hand side here. I've noted two down here. The top one is for what I would call marginal algorithm performance. You're on the cusp of starting to have problems. What you should really use is the version on the bottom right there. And in there, all you've got is the size of your particles, D50 value of either the sand or the seeding particle that you're using, and you've got the model dimensions in there, and then of course the size of your images in pixels. So you can chuck numbers in there, play around with it, and get a feel for what sort of resolution is possible for your particular choice of camera. Now, after the fact, you can also check for evidence of peak locking, and you might do this by plotting histograms of the displacement magnitudes. And if you've got a peak locking problem, what you'll find is you get these humpy distributions that start to have humps around integer pixel values. Doesn't always occur at every integer pixel value, depending on the gradient of deformation in your problem. And in this case, you can probably see that they're every other integer pixel value. If you plot the subpixel component of your displacements, you get the picture on the right-hand side. And if you've got a big hump in the middle around 0, you've got a peak locking problem. Right? So this can be checked after the fact as well. So clear evidence of peak locking here. This is data taken from the classical algorithm. And here's a picture of what you should see if you've very carefully designed your experiment and got your particle image size to be an appropriate value. There's no hump in the displacement histogram, and the subpixel displacement histogram is effectively flat. All right, so that's what you're aiming for, and you can check this post hoc. The problem is, by that point, it's too late. So if you've got the first picture and humps in your displacement histograms, then you really want to question what you want to be doing with the data. Qualitative analysis, fine. Quantitative, well, I'd start to be a bit worried. And if you're taking derivatives of displacement fields, you've got big problems. Here's the histograms for that real-world data from the Glass-Bellottini experiment. You can see these massive peaks, right? Huge peaks, huge peak locking problem. If I change the algorithm and I move to the iterative type approach, then there's much less evidence of the peak locking. There's still a little bit there in places, but it's mostly gone, okay? So it's a good way of checking, plotting these histograms. So key points, just to recap. You want to be conservative with your field of view, okay? Don't assume that the best thing for you to do is just image the whole sample. Actually, in the far field, not a lot's happening. It's probably not all that useful. It's sort of wasted resolution if you spend it on too much of the far field. You want to make sure that D on P ratio is a reasonable value for your particular setup. So aim for at least 2, ideally aim for 4. Pick a PIV algorithm that's robust and isn't likely to suffer from these breakdowns of the subpixel refinement. So pick the right algorithm, don't rely on it entirely. Most of the secret is in the preparation and the setup for the experiment. And as I've already hinted at, once you realize you've got a peak locking problem in your data, it's too late, all right? And that's going to limit what you can do with the data. So check this before you go and perform all of your experiments. So ideally, check your minimum DRP criteria, and then after your test, as a final check, go and check your displacement histograms. And what I would recommend is you do this at 1G on the lab floor with an exact mock-up of your experiment. Do an experiment, in spite of the stress field being wrong, get some images you can analyze and just check that the output you're getting is as it should be before you go and do your full sequence of experiments. Now, let me just have a look at time. About halfway through. Okay, good. So where are we then? We've got our equipment set up. We've got our camera in position. We've got an appropriate field of view. What we now need is nice, even illumination. We want to make sure it's even across the whole field of view. What we really want to avoid is reflections, right? And I'll show you some examples of reflections in a minute. And essentially, what a reflection does is it creates a hot spot in the image where the integer pixel values or the values of each of the pixels in terms of an 8-bit image, 0 to 255, are all going to saturate at one end of the spectrum. And we want to avoid that. if you've got control points, you want them to be really high contrast, and you want them to give you a non-biased centroid calculation when you're trying to find the center of the control point. And I'll show you some examples of good and bad control points in a minute. You want consistent illumination. So you don't want the lighting conditions to change temporally throughout the day. So I always advocate shrouding it in a nice black shroud. Rely only on the lighting that you're controlling and not the ambient lighting around the problem. If your window that you inherit happens to be scratched, then either repair the scratches or replace the window. Find a friendly machinist for repairing the scratches. They might moan at you about polishing the perspex, or they might even tell you it's not possible, but it is possible. It's not an enjoyable process, but it's absolutely worthwhile, because if you've got a scratch on your window, the PIV algorithm will get confused by that, and it will hone in on that scratch and it won't let go of it. So here's some examples of good and bad practice with respect to these aims, okay? So these have been sent to me over time by various people having issues with their analyses, and they've had the good grace to allow me to use them as examples here. Now, this case from Yusuf Ansari's got lovely even illumination and exposure, right? The sand looks the same all the way across the problem, which is great. There's no evidence of significant reflections, which is good. But if you look at the control points, there's minimum contrast between the white and the black regions about which we're going to centroid. So this makes centroiding really, really hard. And what Yusuf was struggling with was the photogrammetric correction algorithm was all over the place as a consequence of these markers being very, very difficult to calculate centroids for. So the centroiding process in this case would be difficult. Here's another example from Yara Franco. Again, beautiful even illumination and exposure, all very good. There's no evidence of significant reflections, which is great. The control point contrast is very good, but the execution of the control points is not as good as it could have been. So in this case, you can see here, if I took the centroid of this blob, it's going to be biased as a consequence of that bleeding at the bottom of the black part of the control point. And again, this made the whole process of photogrammetric correction rather difficult. So, you know, most of the way there with this setup, and then just this last little detail created problems. Here's an example from Yang in Germany. Again, nice even illumination and exposure. No evidence of significant reflections, which is good. There's a control point panel in the middle of this annulus of soil, which is great. It's used to scale the measurements, but not to correct for image distortion. And in this case, I think that's fine, because this soil is sort of constrained radially. The movement of the soil is very, very small. And so as I hinted at earlier, the photogrammetric corrections are not really that important. The downside is this is in a lab environment relying somewhat on ambient light. So throughout the day, the ambient light is changing, okay? Now, the algorithm that we use in GeoPIV-RG can account for this to some degree. It's semi-invariant to the ambient overall light intensity in the image, but it's not perfect. And this was really, really quite challenging, even in spite of using that zero normalized cross-correlation algorithm. So shroud the sample, use artificial light, control it at all times would be my takeaway from that one. Here's an example from Orestes Adamidis at Cambridge at the time. We've got nice even illumination and exposure. Control point contrast is excellent. However, you've got these two great big white spots in the far field, which meant that that part of the simulation just couldn't be used in the analysis. So they're annoying. You've got to mask them out. You've got to sort of guess how much you've got to mask out. You want to keep it to a minimum naturally. It just makes the whole process of analyzing this data more laborious than it ought to be. Now, it's not always avoidable to get rid of these reflections entirely. In this case, we've improved the situation in Cambridge by using larger, more diffuse light panels and more of them. But particularly if you're performing the sort of dynamic test that Yanis is performing here, the lighting becomes even more critical. And this was a dynamic test, which is why Orestes couldn't do without these lights and why he had to suffer the effects of the reflections. So in general, better to use light bars and diffusers than spotlights, but sometimes needs must. Here's an example from an undergraduate at UWA called Pete McGinty. He was looking at iceberg ploughing. The illumination's fairly even. It's a bit underexposed in my view, which will lose some signal signal relative to the background noise in the image. The big problem here, though, is there were masses of scratches on this box. And this was sort of only really discovered when he was in the depths of analysing the data. And what happened was subsets would get stuck on the scratches and would pollute his measurements as a consequence. So time for a new window. In this case, this one was so far gone, it got chucked in the bin. But you can also skim them, have them repolished if you've got a friendly machinist. Here's another example from UWA, from a postdoc I worked with, Raphael Ragni. Again, even illumination and exposure, the control point contrast is really, really good. There are some reflections from the lighting, but they're limited to areas of the image that we're not really interested in. So you can see them at the top of the image there. So that's not so much of a problem. But what is a big problem is he's used too much seeding. Right? So this sand ordinarily is just silica sand. It would be a light brown color. He's decided he's going to put some dyed black sand into that mix. And in this case, he's put too much in. And the reason that happened in his case was he was doing this experiment with a pore fluid called methocel. And oddly, when we back saturate the sample with methocel, what looked like a really nicely textured sample in dry sand just turned into this black mess. All right. So you've really got to mock up your exact experiment. You can't take shortcuts at any point. So the seeding needs refinement. I'll talk about that a little bit more later on, and I'll give you a process you can follow to achieve that. This is another example of lighting from Yahya Nazhat, who at the time was at the University of Sydney. Got nice even illumination and exposure. There's a minimum number of control points, which you can see down the left and the right-hand side of the image here, these sort of cross hatches in black and white. That's fine. It's just going to mean that he'd be limited to correcting the image for scale effects and not necessarily lens-induced distortions, but that's perhaps not a big issue. So those points are fine for scaling. However, the big issue here is he's taken a picture of the whole model. And because of the size of his sand grains, the D on P ratio was marginal. It's pretty much exactly 2. And when he used the old classical GOP-IV algorithms back in the day, we got peak locking problems. And so here's another example experimentally of that peak locking issue. The displacement's biasing to integer pixel values. And when you take derivatives of the displacement fields, you get these funny strain fields. And again, this data got published in Granular Matter, I think. And at the time, they were proposing that these bands were effectively like shock waves moving through the soil. In fact, they're just a figment of the breakdown of the analysis, right? So be wary. Peak locking can make you think things are happening when they're not. So I promise that's the last time I'll mention peak locking. So we've got our camera in position, we've got some nice lighting. Now we need to work out the appropriate settings for the camera. And my general approach is to find the smallest aperture for which the lighting facilitates sufficient exposure. So slightly curiously, a big number on the aperture means a small aperture in reality, right? So f1.4 is a very big aperture, f16 is very small. We want the smallest possible aperture, so the biggest f-stop, in order to achieve good focus across the image, okay? So you've got to play around with the aperture size and the exposure time. There's a balance here because you might want a small aperture to get good focus, and I'll show you the effects of focusing in a moment. But that's going to mean a longer exposure time because you're letting less light into the camera. And at some point, if you're modeling a problem which has significant deformation rates in it, you're going to start to get blurring of the image as a consequence of exposing the image over a significant portion of the experiment. So it's a difficult balancing act. You've got to go back and forth, and you've got to find a balance between the right f-stop, ideally small, and the right exposure time, also ideally small. So larger f-stop or aperture is going to allow more light into the lens, give you a shorter exposure time, but it's going to give you a narrow depth of focus. So on the left, I've got small aperture and long exposure time, large depth of focus. You can see all of the flowers in this image are in focus and sharp. And on the right-hand side, we've got a large aperture and a shorter exposure time and a correspondingly narrow depth of focus. Now, for what we're doing in the lab, we're modeling a plane. We're imaging a plane at a consistent distance from the camera. So you can find a balance point. You can find a sweet spot between these two extremes quite nicely. You just want to make sure that for whatever aperture and exposure time you choose, that you can get good sharp focus across the whole image. So we've now got a camera set up, we've got good lighting, we've got an appropriate field of view, we've gone and set up the aperture and exposure time on the camera, and we want to take some trial images now of our mock-up sample. Once we've got those trial images, we can compute some measures of image texture quality, if you like. And here's a few examples here. One thing we might do is we take all of our subsets, and for each of them, we calculate a standard deviation of the pixel intensities of the subsets. And this will give you a sort of crude measure of the level of contrast that you've got. And our suggestion is you aim for a value that's greater than about 15, okay? Another measure might be to take what's called the sum of the square of the subset intensity gradients, or SIG. And this is looking at the contrast frequency. And in general, higher is better, but only so long as that D on P ratio is appropriate. And in general, you want to aim for about 1 × 10⁵ or greater in that particular case. They're two subset level quantities, but you can also look at the image as a whole and calculate the mean intensity gradient, which is just a variant on SIG developed by the same research group in Beijing. And that will give you a sort of global, quick, rough measure of the contrast frequency in the problem. Now, you don't need to calculate these yourselves. If you're using GeoPIV-RG, then these are actually calculated in the mesh output file. They're the last columns in the output data. And so you can plot those values across the population of subsets in order to check that you're somewhere near these criteria. Here's some examples of low and high image quality. So on the left, we've got an example of low standard deviation of subset pixel intensities and SIG. That's going to give us really low precision measurements in spite of the particle image size being okay in that instance. And on the right-hand side, we've got 3 examples of high values of the standard deviation of the subset pixel intensities and the SIG value. Okay, so you want to aim for texture that looks more like what we've got on the right-hand side here. And in this instance, we've got the golden shaped subset is a glass Velocimetry experiment. And then we've got a seeded sand and a seeded clay sample on the right. So as I said, these are both calculated by the meshing function that we provide. So you don't need to write out those summations on the previous page. And in essence, then, what you want to do in terms of setting up your PIV analysis is identify the minimum subset size that's going to result in adequate subset texture quality measures. Right? So you can control these outputs to a degree by increasing or decreasing your subset size. And the optimum value is the smallest value that gives you good numbers for these quality measures. So if necessary, you probably want to refine your image texture to optimize the image quality. And it's dependent on 2 things: subset size I've already mentioned, and also the inherent image texture. We can fiddle with one, the subset size, retrospectively, but the second one is entrained in our images. Once we've got the images, there's not much we can do to influence the image texture. Now, in general, in the early days, people used to try and use soils that had nice natural texture. So Dog's Bay sand was used in the early GeoPIV experiments back in Cambridge because it has particles of different colors, which in an image sense give you different intensities in the matrix of pixel intensities. These days, people tend to use either dyed sand or what we call modeler's flock, used by railway enthusiasts to make model Hornbury railways. You can get it in a variety of colors: black, green. They're typically good colors to use for these measures. And you might want to use different colors for different layers so that you get some instantaneous feedback about what's going on in your experiment. But the big question you've got to answer is how much? How much is the right amount? And so what I'm showing you here is a sequence of images on the left for kaolin with green modeling flock, and on the right for kaolin with dyed black silica sand. And we want to know which of these images in the sequence is the optimal amount of seeding to use in practice. So this is a laborious process, and it's one I suggest you follow at least once to get a good idea for your particular setup as to what the appropriate texture might be. And what we do, in a sense, is we just define this artificial seeding ratio. So we take the mean pixel intensity in our current image, we take the mean pixel intensity in the image with 0 seeding, ASR of 0, and the mean pixel intensity in an image saturated with seeding, so an ASR of 1, and we define what the ASR is for our sequence of images moving left to right on the top there. What you find is if you plot the standard deviation of the measurement errors for a population of PIV data, you find that it correlates nicely with this artificial seeding ratio. And what I'm showing you here is the standard deviation of the subset pixel intensities, okay? So on the left-hand side, I've got no seeding, I've got relatively poor contrast, and there's a small band of image intensities that is encapsulated in the subset. As I add seeding, I rise towards a peak at an ASR of about half, and then when I keep adding seeding, I start to lose contrast again, and I fall off the other side of this peak here. And this is true for both of these types of seeding. So higher standard deviation is going to give us higher contrast, and in principle, that gives us more precise PIV measurements, as I'll show you now. So what I'm plotting here is for 3 different subset sizes, 25, 50, and 100 pixels, I'm plotting the standard deviation of the measurement errors for what we call a zero displacement analysis. That's where I try and measure the displacement from my reference image to my reference image. So I know the displacement should be 0, and the measurement error is what I'm plotting on the left-hand side, but as a standard deviation of the population of the measurements. And basically, a low value is good, all right? So we can see as I'm adding seeding, as the contrast is increasing on the horizontal axis, the errors are reducing. And you can see if you've got a keen eye, particularly if you follow the green data on the left, that the errors are coming down to a minima and then rising back up again. And that's as I go from no seeding to optimum seeding and then back to overseeded. All right, so we want to find that sweet spot. So higher standard deviation of subset pixel intensities gives us increased measurement precision. So now I'm plotting the artificial seeding ratio from the first set of graphs against the errors. And you can see we've got a nice trough now. And what we want to do is pick the ASR value that gives us the bottom of that trough. That's our optimal artificial seeding ratio. And now what we can do is just go back, find that image, print it out, put it next to our model, and then recreate that every time we make a sample. All right, and we know then we've got the optimal seeding. And here's the effect in terms of measurement precision. This shows you the importance of seeding, because as I suggested, back in the early days, people used to try and use sand that had nice natural texture. But actually, this data here is showing that even if you take a sand, applying additional seeding to it is going to improve the measurement precision quite significantly, by a factor of about 2.5 in this case. Okay? So even if you think you don't need seeding, it might well be beneficial to add it in. Looking a bit more closely at why the precision improves with optimized seeding, what I've done here is I've taken 4 subsets from 4 different images with different seeding ratios. So on the left-hand side, no seeding, on the right-hand side, optimal seeding. And I've plotted histograms of the normalized frequencies of the pixel intensities across the subsets. And you can see the 2 big peaky values on the right-hand side are where we've got no seeding, and we've got a very narrow bandwidth of pixel intensities that are encapsulated in the subset. And by adding the seeding, we've just flattened out that histogram and spread it out, and we've ended up with a much more balanced distribution of pixel intensities and therefore higher contrast in the image. And that ultimately is what causes an improvement in our measurement precision, because our algorithm has got more information to play with. Okay, in essence, that's what it boils down to. So, sample preparation, some key points, and there'll be, I think I'll be finished in about 5 or 10 minutes. There'll be plenty of time for some questions or even an early lunch. The big take home that I want you to take from this is the addition of artificial seeding really ought to be optimized at least once. It's a pain. You know, those couple of examples I gave you there were a couple of days spent in the lab, disassembling, reassembling, applying a bit more seeding, reassembling, taking another image. It's a horrible process, but I think it's genuinely worthwhile in order to find the optimal values at least once. And you can see the effect on measurement precision is really quite significant. Once you've done the process once, you can just repeat it qualitatively by comparing your optimized image from your initial setup of the apparatus. You can just apply that qualitatively side by side in future experiments. Now, if you were sharp, as I rattled through that data there, you'll notice that the effects of the seeding are even more significant the smaller the subsets get. And ideally, you want to be using small subsets with close spacing so you get really nice high resolution displacement and strain fields from your PIV analysis. So help yourself by optimizing the seeding so that you can take advantage of increased spatial measurement resolution. Sand models also require seeding. It's worth the time and effort to add the seeding to sand as well, but the choice of seeding is definitely soil specific. The final takeaway is too much seeding is as bad as none, right? So you don't want to make the mistake that Raf and I made by applying what we thought was an optimal amount of seeding, then getting into the centrifuge, back saturating with methacel and finding actually, because we hadn't mocked up the whole experiment in all of its detail, we ended up with bad texture in the first experiment we performed. So mock up your tests exactly as you want to perform them in the lab. And really, the thing I want to hammer home is the PIV analysis is all in this setup and preparation. All right, I've now been talking for over an hour, and I haven't even touched on PIV analysis. I haven't even got to how you would run the algorithm and interpret the images, because actually that's the easy bit. If you get this bit right, that bit's trivial. And I never hear from people with good images. I never get an email from them. The good images are easy to analyze. The people I hear from are all the examples I gave you earlier, where there were problems in the test setup and preparation that they then came to me and asked me if we could fix it somehow, okay? So finally, just to finish off, how do you actually run a PIV analysis? So you've got your sequence of images, you need some software. Now, these packages are not actually that difficult to write. They're not very complicated. The classical algorithms like the original GeoPIV are just simple FFT-based algorithms. You can write them in MATLAB or Python with a handful of lines of code. Right? There's not much to them at all. So you can roll your own. The iterative approaches are a bit more involved, but to be honest, even then, a couple of hundred lines of code, you can write your own version. But equally, if you can't be bothered with that, you can download GeoPIV for free, and it will do it for you. There are other alternatives out there that have the same underlying algorithm. So NCore is written by the guy that I co-authored the paper on GeoPIV with, a guy called Justin Blaber. It's the same algorithm. It's just targeted at a different subset of solid mechanics modeling. He's looking at very small deformations. We had problems associated with large sequences of images and large deformations, which meant we had to approach the analysis in a different way. But you can use either of these. They're very good. NCore's got a really nice GUI, which if you don't like operating things from the command line in MATLAB, you can use. This picture is probably going to change in the next 6 months or so, because we've now moved development of GeoPIV to Python. And so we're hoping in the next few months we'll be releasing a Python package via pip that you will be able to one-line install and then use, that is ultimately a lot more usable, but we're just in the final stages of validation of that. So there's a bunch of online training available on the GeoPIV website. So if you go to the download, there's an example data set. It's exactly the same data set that I've been using for various examples throughout this talk. There's about a dozen how-to videos that you can follow along with. There's no sound on these videos. They're totally silent. All you need to do is be able to read English, and there are pop-ups that tell you what you're doing at various points in time. Mainly, there's no sound on these videos because I can't stand the sound of my own voice, and so I just did them mute. They take you through the whole process. So they take you through setting up the analysis, getting some output data in pixel terms, performing the photogrammetric corrections, calculating strain fields, even basic plotting of displacement fields and strain fields are there. So you can play around with that, follow the how-to videos, get the basics out, and then the next thing to do is to just be creative and make your own plotting or animation subroutines. And really, you're just limited to your own imagination there, okay? You can plot cross-sections of displacement and strain fields. And well, you've seen some analyses that I gave earlier on in this talk anyway. So that's it from me. I just want to finish on this, though. You can see here, I've got 2 slides at the end about running an analysis. I've not actually shown you a single command. There's videos to help you through that. But I do this purposely because I really want to make it clear to you that it's not about the analysis part. That's the tiny little bit at the end. But all the preparation is the key part. Get that right, the analysis is easy. All right. And people that have good images, as I said, I never hear from them. I only hear from people that didn't put the time into the preparation and setup at the end. So at this point, I finished well early, I think. So I've got time for any questions. Has anybody got any questions or comments?